So in this video, we're going to talk about determinant theorems. So I'm assuming that you know how to calculate a determinant before you watch this. If you don't, I suggest just going back and reviewing that. So there are 7 determinant theorems that we're going to talk about, so I'm just going to jump right into them. So the first one says that if every element of a row or column of a matrix is 0, then the determinant is equal to 0. So for each determinant theorem, I want to just present an example that explains what that means. So here is a 4x4 matrix that I want to find the determinant of. And so whether or not you know how to calculate a 4x4 matrix, so just think about this top row here. So as I expand along the top row, since these are all zeros, all of those minors or submatrices that we would multiply against these zeros, well, they're like the answer doesn't matter, right? Because all that you're going to end up with is 0 minus 0 plus 0 minus 0. So this whole thing will just end up equaling 0. So the second you see either a row or column of zeros, then it is just a slam dunk. The whole thing just equals 0. Theorem 2, if the rows of a matrix A are the corresponding columns of a matrix B, then the determinants are going to be equal. Okay, so to demonstrate this one for you, so here I've got my first matrix. It's a 3x3 matrix. And okay, so let's see, where would it be easiest to expand along? I would say either around this row or this row. I'm going to expand along the middle row. So, okay, so the first entry is going to be equal to 0, and I don't have to worry about anything else with the submatrices because 0 times the minor will just equal 0. So up next, I'm going to come to this one. So remember, you go plus, minus, plus, minus, plus, minus. I'm just talking about what the signs of the cofactors are. I talked about this in my last video. So this one will be a plus. So this is plus 1 times. So, okay, if I expand along this, so here's my cofactor, so I can see what my minor will be. 1, 3, 3, 0. Okay, so there's that expansion. Get rid of all that, and then we can continue along to this one. So this will be minus 1 times, and then if I just look at what's left over, this will be minus 1 times 1, 0, 3, and 2. A lot of zeros in this matrix, so at least it'll be a little easier to calculate. So let's see, I'll move the equal sign up here. Okay, so then this is going to equal really 1 times, let's see, 0 minus 9 minus 1 times 2 minus 0. So I get negative 9 minus 2, so this equals negative 11. Okay, so there's my first determinant. So I want you to appreciate what I did. I took this row and now I made it the column, okay? I took this row and now I made it the column, and then I took this row and I made it the new column. So we're going to calculate the new determinant in this case, and let's see. I can really still expand along this column, so that's what I'm going to do. So if I start here expanding, and just to go through the cofactors here, so this will be minus, plus, minus. So, okay, so starting with 0, well, we know that 0 will still just be 0, so I can just leave that alone. So this is minus, plus, minus, so this will be plus 1. So check out what happens. If I look at what minor is left over, this is 1, 3, 3, 0. And then as I continue down the column, down to here, so this will be, this will be minus 1 times, so the minor that's left over in that case is 1, 0, 1, 0, 3, 2. Okay. So if I go through and I calculate all of this, let's see, what am I left with? So this is going to be 0 plus 1 times 0 minus 9 minus 1 times 2 minus 0. So check it out. This is negative 9 minus 2, which still equals negative 11. So that's what that theorem is guaranteeing. If you notice that the columns are really just the like transposed into the rows, you're going to have the same determinants, and we have just proven it. So that is what this theorem was talking about. Okay, so let's move on to theorem 3. So if any two rows or columns of a matrix are interchanged, then the determinants are negatives of one another. Okay, so for this example, so notice I have these two determinants, so I literally just flip-flopped the rows, and we're just going to see what happens with the value of the determinants. So for this first one, so I've got 2 times 6 is 12, and then minus 5 times 4, which is 20. So this equals negative 8, versus this determinant, 5 times 4 is 20, minus 2 times 6, which is 12, so that equals 8. So they are negatives of one another, negative opposites, whatever you want to call it. Okay, that's what that theorem's getting at. Theorem 4. Suppose a matrix B is formed by multiplying every element in a row or column in a matrix A by a real number k. Then B equals k times the determinant of B equals k times the determinant of A. Okay, so moving on to the associated example. So let's just start by calculating this first determinant. So if I calculate this out, I have 2 times 6, which is 12, minus 3 times 1, which is 3. So 12 minus 3 is equal to 9. Okay, so notice what I did, or what the difference between this determinant and this one is. So in this row, I basically took the first row and I just multiplied it by 4 to get this result. So let's check out what the value of this determinant is. So 8 times 6 is equal to 48, and then 3 times 4 is equal to 12. So 48 minus 12, that's going to equal 36. Now, remember, this row was found by taking this row and then multiplying it by 4. So now look at the connection between the two determinants. 36 is equal to 9 times 4. So that is what this determinant is getting at. If you know the value of this determinant and then you just multiply a row by 4, instead of recalculating the determinant, you can just rely on the fact that if you know the value of the first determinant and you can see what that row was multiplied by, you could just multiply the value of that determinant by that value. So that's what that one is getting at. Theorem 5. If two rows or columns of a matrix are identical, then the determinant will be 0. Okay, so I have here just a little 2 by 2 matrix. So notice the rows and columns in this case are identical. 4 times 4 is 16. 4 times 4 is 16. So you just get the same values, that'll equal 0. This is always true, whether you have a 2 by 2 matrix or something larger. The second you see a column, 2 columns or 2 rows are identical, you can just automatically say that it equals 0. Okay, changing a row or column of a matrix by adding a constant times another row or column does not change the determinant. Okay, so what I want to do for this one is I'm going to start with a matrix A. So the first thing I want to do is I just want to calculate the value of the determinant here. So this will be matrix A, so the value of the determinant will be 8 minus 10, which equals negative 2. Okay, so now I want to create a matrix B, where what I'm going to do is I'm going to take row 1, and I'm going to replace it by taking row 1 plus 3 times row 3. So let's make matrix B. Okay, so I'm going to take row 1 and then plus 3 times row 3. So I want to just be really clear what I'm doing here. So I'm taking these elements, and then I'm taking row 3 and taking 3 times them and adding them to that row. So I'm really doing just one of the row transformations that we're capable of doing. Okay, so if I do that, 16, 5, let's see, 26, and 8. So now, what's the value of this determinant? So this is going to be, so if I take 16 times 8, that's 128, and then 5 times 26 is 130. So what is the value of this determinant? It's still equal to negative 2. So even though I did that row transformation, notice that it did not change the value of the determinant. The determinants were equal. Okay, and finally, the last theorem we have is if a matrix is in triangular form, which means that you have all zeros either above or below the diagonal, I'll show you what that means in a second, then the determinant is found by multiplying the elements down the diagonal. Okay, so for this one, so here's diagonal form. you've got numbers down the diagonal, and then from that diagonal, you have all zeros either above or below that. So it's like you have like a triangle of zeros. That's kind of the way I remember it. Okay, so think about just what it would mean to expand for the derivative here. So if I would expand along this set of zeros. So what ends up happening is, well, let's do it by hand, I guess. So what I would have here is, to do this, I'd start with the 1. And so I'd have 1 times this little minor. Okay, now maybe you weren't aware of how to do a 4x4 matrix, but you still take, 1 times the minor. So now with this matrix, so now I would want to expand along this line, right? So check out what that looks like then. So I have 1 times, so now we'll take 5 and we'll cross all this out. 5 times this minor. And if I keep going with that, what does this come out to be? This will come out to be 1 times 5 times 2 times 1 minus 0. And notice that everywhere else in this matrix, I don't have to expand along the rest of this row because I have all zeros here. And then for this 3x3 matrix, I don't have to expand along the rest of the row because I have zeros here. So this calculation that you see here is all that I have to do. And so what this calculation really comes down to then is 1 times 5 times 2 times 1, which equals 10. Now, let's back up for a second here, and I want to appreciate then what this theorem is saying. Rather than us having to do all that work, notice those are just the numbers down the diagonal. And what this theorem guarantees is that instead of us having to go through all the work to calculate all this, we can just multiply straight down the diagonal because we know that that's how this is going to work. So that's what that particular theorem is getting at. Okay, so what's the deal with having all these determinant theorems? The point of the determinant theorems is to make your life easier, actually. So when you have a determinant, a lot of times what you're going to want to do is you're going to want to manipulate the determinant using the determinant theorems and see if you can make the determinant easier for yourself. Because with the way that this is sitting, we've just got a lot of work to do with this. I know we've got a couple zeros in here, but maybe we can make it just slightly easier. So the way that I think of when I look at this is, how could I make this easier? Well, I can really easily get a 0 right here by using one of the row transformations, right? So what I could do is I could take row 1 and then I could take 2 times row 2 and add it to this row, right? So I can do a little row transformation. So let's do that. So if I do that, this is going to give me now, so -4 plus 4, this row will be 1 plus 0, and then this row will be 4 plus 2. So here's what's going on in my row transformation. Okay, so if I just clean that up, what does that look like? So then that becomes, let's see, I'll write it over here. This becomes 0, 1, 6, 2, 0, 1, and 0, 2, and 4. Okay, so I did a row transformation, and how does that row transformation impact the value of my derivative? Well, that was Theorem 6 that I just used. This one is one that you use a lot, actually, with determinants. So this does not change the value of the determinant. We just saw an example proving that, right? So I know I can manipulate this determinant and make it something easier. And so now, let me clear some space. Okay, so now looking at this, so where would I want to expand this derivative, or determinant? I would want to expand along here, right? Because I've got a 0 here and a 0 here. So this becomes much easier. So when you're working with determinants, you can freely leverage some of the determinant theorems to make your life much simpler. So what I'm going to have then is, so let's see, this will be plus, minus, and plus as far as the cofactors go. So I have 0. I don't have to worry about expanding along the minors or finding the minor. Then I move on to the 2. So let's see, what do I have for the 2? So I have minus 2, and my minor in this case will be 1, 6, 2, and 4. And then I have plus 0. And again, I don't have to expand. So look at how this, like doing that little row transformation, it saved me a bunch of work. And so when you're working with those 3 by 3 derivatives, this is how you make them much more tolerable. And then I can just finish calculating this. So let's see, this will be negative 2 times negative 8. So this just equals positive 16. So that's one way to use the determinant theorems and just to make your life easier. Now, the other way that you use the determinant theorems is just to remember what they say. And so in this case, like with this determinant, so I just say, oh wait, I've got a column of zeros. So just done, no other work to do. Boom, it's just going to be equal to 0. So that's kind of how you want to leverage those theorems. Some of them tell you how to make your life easier. Some of them tell you manipulations you can do to make your life easier. And that's really the name of the game. Okay, so I'm going to leave it there, and I will talk to you guys in another video.